Hi, welcome back. In this video, we're going to prove a theorem about systems of linear equations, and then we'll use the theorem in an example. So Theorem 4.19 says the following. The system, the m by n system ax equals b, is consistent, meaning it has a solution, if and only if that vector b on the right is in the column space of the matrix A. All right, so remember, A is m by n, so x is from Rn, the unknown or the solution vector x is from Rn, and when we multiply an m by n matrix times an n by 1 matrix, we get an m by 1 matrix, and that means B is in Rm. So the columns of A also are in Rm, because remember, A has n columns and m rows, so each column has m entries or m components. So the columns are in Rm, they span a subspace of Rm, and we want to show that this system is consistent if and only if B is actually in the column space of that matrix. All right, so let's start by writing out. So our proof, we're going to write out the product. So here's the matrix A. It has m rows and n columns. Here's the matrix X. It has n components, x1, x2, up to xn. And then the matrix B has m components, b1, b2, up to bm. All right, so this is consistent, means that that equation is true about A, X, and B. So if this equation is true, then that means that the following equation is true. So that's consistent, means that this, so when I do the multiplication on the left, when I multiply that m by n matrix times the n by 1 matrix, we get an m by 1 matrix. And the entries are a11 times x1 plus a12 times x2 plus up to amn times xn. That's the first component. The second one is a12 times x1 plus a22 times x2 plus dot 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 plus a2n times xn. Those are the first two components. And we keep doing that multiplication. It's just matrix multiplication. The last component is the sum am1 times x1 plus am2 times x2 dot 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 amn times xn. It's just matrix multiplication. So the system is consistent means that this vector, this is now an m by 1 matrix, or a vector from Rm. This vector has to be equal to the B vector, b1, b2, up to bm. So those two vectors are the same. And what does that mean? Well, we can rewrite the left side. The matrix on the left side, or vector on the left side, can be rewritten as x1 times the column vector a11, a21, up to am1, plus x2 times the second column vector a12, a22, dot 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 am2. And we keep going, and the last term is xn times the last column, a1n, a2n, amn, and that's equal to the B vector. So what we've done is we've done the multiplication on the left side, the matrix A times the matrix X. We got a m by 1 matrix. We broke it up and wrote it as a linear combination of the columns of A. And that's what it means to be in the column space of A. All right, let's use this theorem. So here's problem 4 from a worksheet from class. This says, Determine whether the system has a solution, and if it does, write the solution in the form x equals a particular solution to the system plus a solution to the homogeneous system. So we have a non-homogeneous system. So we want to use the theorem we just learned to see if it's consistent. So if we just write down the augmented matrix for this system, we get 2, -4, 5, -7, 14, 4, and 3, -6, 1 for the coefficient matrix. And then the last column, the augmented part, is 8, -28, 12. And so the columns of A are A1, A2, A3, and then B is the last column. And we can see very easily that B is just 4 times the first column, 4 times A1. So B is clearly in the span of the columns of A. So B is in the column space. So according to the theorem we just learned, that means that this is a consistent system. So the system has a solution. All right. So now let's find the solution. Let's get the reduced row echelon form of that augmented matrix. Either using Gauss-Jordan elimination or technology, we get the following. We get 1, -2, 0, 4, 0, 0, 1, 0, and then a row of zeros at the bottom. So the first row gives us the equation x minus 2y is equal to 4. The second row gives us the equation z equals 0. The first equation, solving for x, we get x equals 4 plus 2y. So we get just one free variable. Y is our only free variable. So we can use a parameter s, and we can write our solution vector as 4 plus 2s, s0. All the solutions look like that. And now we can see that there's a constant vector plus a scalar multiple of another vector. So let's write that. So the constant vector is 4, 0, 0. And then we're adding s times 2, 1, 0. So the constant vector, 4, 0, 0, that is a solution to the system of equations. And 2, 1, 0 is a solution to the homogeneous system. All right, so here we've found that the system is consistent by showing that B is in the span of the columns of A. And then we found all the solutions and wrote them as, we decomposed the solutions into a sum of a particular solution and a scalar multiple of a solution to the homogeneous system. All right, so I will see you in some other video.